Okay, the wind is a little strong today, so I heard a little too much noise in the previous podcast, so I have partially closed the window. Sorry, I love this weather with this wind. If you lived in Mumbai and you experienced the hot temperature, you know how much you love the cooler temperatures that last a little too short in a year. Okay, so we started with this Coriolis effect, and now we want to show how it works. We said here, by looking at the figures and looking at this displacement east and west, how the deflection happens in the northern hemisphere to the right of the direction of motion, whether you are going south and north or east and west. How do we explain that in terms of equations? So if Coriolis is the only force acting to accelerate the fluid, in which case the speed is not going to change, but the direction is going to change. So du dt and dv dt are still non-zero, and the zonal velocity has to change in a way that it has to acquire a meridional component when Coriolis acts. So simply speaking, du dt becomes equal to f times v, where f is the local Coriolis parameter. So f is 0 on the equator because you are moving linearly. There is no rotational effect on the equator. As soon as you step off into the northern or southern hemisphere, Coriolis begins to act, and it increases towards the poles because your distance at the surface from the rotational axis decreases as you go from the equator towards the poles. So the f also increases, and the local Coriolis parameter turns out to be just 2 omega times sine theta, where theta is the latitude. So sine theta is 0 at the equator, f is 0, sine theta is 1 at the poles, so you get rotational effect to be 2 omega. There is some ways to explain why the rotational effect is 2 times the rotation rate, which you can look up elsewhere on Google or so. Okay, so similarly, v, meridional velocity, has to be deflected to the east or west depending on which way you are moving. So that gives us minus f times u to be the meridional acceleration term due to the Coriolis effect. So you can work this out looking at how f changes so depending on whether the water is moving north or south, you want to acquire eastern or western component, which is explained by putting the negative sign there. So we can pull the equation together now using again our ideas of mixing eddy diffusivities in the horizontal and vertical. So acceleration due to just momentum mixing. Now we are talking about momentum diffusion, but it's eddy mixing, eddy diffusivity, eddy viscosity, and not molecular viscosity. Okay, so as we wrote for salinity and temperature before, we can write the acceleration terms due to the eddy mixing as horizontal eddy mixing coefficient times grad squared horizontal times u plus vertical eddy momentum mixing or eddy viscosity times del squared u del z squared. We are using diffusivity, viscosity, and mixing all together here because diffusivity is typically used for tracers like temperature and salinity, and viscosity is used for momentum because it's related to motion, right? So these are eddy viscosities, and we used eddy diffusivities for temperature and salinity. Of course, this is a Laplacian operator del squared del x squared plus del squared del y squared, and we have seen these expressions before. And as we said before, the horizontal eddy viscosities tend to be orders of magnitude different than vertical eddy viscosities, as we will see again later, but you can also look that up. Just turns out that in strongly vertically stratified fluid, horizontal motion, actually it is along constant density, but typically we end up projecting onto horizontal and vertical, and there is a lot of literature explaining why we should think of motion along constant density layers or constant isentropic layers in the atmosphere, because energetically that's how things work, and cross isopycnal fluxes and mixing tend to be very different, and so on and so forth. So without getting distracted too much, digressing too much in this introductory course, just think of horizontal and vertical directions, and remember that horizontal eddy viscosities tend to be much larger than vertical eddy viscosities, orders of magnitude different. But these are the vertical and horizontal shear terms. If there is a vertical shear, that's like a potential energy which can be mixed and converted into momentum, eddy kinetic energy, for example, and similarly horizontal shear acceleration happens because of that potential energy conversion as well, because of eddy mixing. Okay, so in the real world, it's the wind stress at the surface that is putting momentum into the ocean. So the zonal momentum is typically written as air density times some drag coefficient, measure of friction of how momentum gets transferred into the ocean, times UA squared, which is the air velocity, wind velocity that is putting momentum in, and similarly meridional wind stress is rho A times CD times VA squared. And in general, we tend to measure wind stresses. For example, there are scatterometers which take wave properties observed from space and convert them into wind stresses. So wind stress themselves, the gradient of the wind stress from the free atmosphere, or let's say from at 10 meters down to the surface of the ocean, is the gradient del tau x del z, and the density is rho, and that is related to the shear that we talked about, del squared u del z squared, or the mixing of the momentum. So Az del squared u del z squared and Az del squared v del z squared. So those two we relate. These are considered are bulk formulae. So there is actually mixing happening at the interface of the air and the water, but we want to represent it in terms of observable variables like the vertical gradient of momentum in the water and vertical gradient of wind stress in the air, and how that momentum is transferred into the water, and so on and so forth. So you can imagine that wind stress is dragging the water at the surface and it's penetrating the ocean. At some point the wind stress doesn't reach below certain depth, which is typically the scale of mixing of momentum within the surface. So here is the illustration of the relationship between wind speed and wind stress using pseudo stress meter squared per second squared from the cross-calibrated multi-platform level data, which is a detail. Each point on the graph represents 1/4 degree grid cell over the world ocean for one of the 12 months of the year 2000. So for a particular year, monthly means are used. There are a total of 6.5 million points going into this correlation here. So pseudo stress is basically wind stress which is converted into wind stress using these transformations of air density and drag coefficient, which are typically measured in the lab, and whether they work in the field, and so on. So lots of details. Again, there is a lot of wind, so there is going to be some sound in the recording. Sorry about that. Maybe I'll close it for the next podcast. Okay, so you can see that as the zonal wind speeds, depending on whether the pseudo wind stress is negative or positive, you get this relation with the pseudo wind stress, which is in meters squared per second squared. Okay, so just keep that in mind, and we'll come back and look at further details of wind stress in the next podcast. Okay.